Good afternoon, my YouTube viewers. It's Crystal here. In this video, what we're going to be talking about is distributions used in hypothesis testing. So there's four main distributions that are used in R for hypothesis testing, and these distributions are the normal distribution, which is sometimes called the Z distribution, the T distribution, which is similar to a normal distribution except that it has fatter tails, the chi-square distribution, and also the F distribution. And so in a previous videos in this playlist, I have actually discussed these four distributions, but these are the four distributions that you're going to use in hypothesis testing. So the first thing we're going to do is we're going to perform a hypothesis test using the normal distribution, which is sometimes called a Z distribution. So what we're going to do is our sample question is we're going to test whether the mean test score of students in a school differs from the national average when the sample size is large. So that means the sample size has to be greater than 30. So the first thing that we want to do is we want to generate a large sample, which is greater than 30. So we're going to set our seed. So whenever you set your seed, that means that every time you run the cell or run the program, the variables will initialize to the same values. So you type set.seed brackets 1, 2, 3. And then N is going to be the number, it's going to be the sample size, and it's 100. Sigma is your standard deviation, and it's 10. And your mu is your 70, and that's your average or your mean. So sample scores becomes R norm. So R norm is a randomly sampled normal distribution. Brackets N is 100, comma, mean equals 73, and SD equals sigma or 10. So basically what we're doing is, although we're setting the sigma up as 10, and we're setting the mu for looks like the population up as 70, in our sample, what we're going to have is a mean of 73. So the mean of the sample is going to be different from the mu. So we're going to perform a two-tailed Z test. So X bar becomes mean brackets sample scores. So sample scores is the normal distribution that with 100 samples, and the X bar is the mean of the sample scores. So basically the normal distribution is sampled 100 times, and the X bar is the mean of that. So your Z stat becomes brackets X bar minus mu, and mu 0, which is 70, divided by sigma, which is 10, divided by the square root of n, which is 100. And your p-value becomes 2 times 1 minus p norm, brackets abs, that's absolute value, brackets z stat. So your p norm is the normal distribution with a probability. So your z stat, and so we're going to print off the z stat, and if the z statistic is greater than 1.96, you're going to reject the null hypothesis. And you're also going to print the p-value. And so if the p-value is less than 0.05, you're going to reject the null hypothesis. So let's come over here and see what our z statistic and our p-value is. So your z statistic is 3.9, and your p-value is really small value. it's going to be less than 0.05. And so since your p-value is less than 0.05, the null hypothesis is going to be rejected. And if the z-statistic is greater than 1.96, which it is, you're going to reject the null hypothesis. So in both instances, we're going to reject the null hypothesis in favor of the alternate hypothesis. So the null hypothesis is going to be that the students' test scores, there's no significant difference between the students' test scores and the national average. And the alternate hypothesis is there is a significant difference between the students' test scores and the national average. So if mu0 becomes 70 as the national average, and the mean of the student test scores is 73, then that means that the student test scores are going to be 3 points greater than the national average. But now what we're going to do is we're going to plot this information on a curve. So curve brackets, d norm, that's the density plot of the normal distribution of x, comma, from -4 to +4 with a line width of 2. Main, which is your title, is two-tailed z-test for mean test score. Y-lab is your label on your y-axis, which is density, and x-lab is the label on the x-axis, is x value. So we're going to calculate our critical values. So crit becomes Q norm, so that's quantile of the normal distribution at 0.975. So what you're going to do is you're going to take the normal distribution and you're going to plot 97.5%. And then we're going to shade the rejection regions. So x left becomes SEQ brackets -4, comma, negative crit, comma, length equals 200. And x right becomes sequence brackets crit, comma, 4, comma, length equals 200. So that's telling you that the values are going to be -4 to +4, and it's going to be based on the negative critical value and the positive critical value. So we're going to put a polygon in there. So polygon bracket C, brackets x left, comma, REV, brackets x left, comma, C. This is a vector that we're creating. Brackets D norm, so that's a density curve. Brackets x left, comma, REP, bracket 0, comma, length x left. So the length is going to be 200, and color is going to be light pink. And then we're going to have another polygon, it brackets C brackets x right, comma, REV brackets x right, comma, C. This is another vector, brackets D norm, which is the density of the normal distribution, brackets x right, comma, rep, bracket 0, comma, length of x right, which is 200. And color equals light pink. And then we're going to add a vertical line for observed z-statistic. So AB line, brackets V means it's a vertical line, equals z-stat, comma, color equals blue, comma, line length equals 2. And then we're going to add critical value lines. So AB line, brackets V means it's vertical, equals C, which is a vector. We're creating brackets negative crit, comma, crit, color equals red, line width LTY equals 2, so I think that's dashed, and LWD equals 2. So now we're going to annotate this chart. And text means you're putting text in there, brackets z-stat, comma, 0.1, comma, labels equals paste 0, brackets z equals, and then it's going to be z stat rounded to 2 decimal points because paste is like is similar to a print command. POS equals if else brackets z stat greater than 0, 4, 2, color equals blue. So we've got our two-tailed z-test for mean test scores, and we created a chart. We've created a normal distribution. So you can see that the light pink is your critical error areas, and you can see that your critical areas are about close to -2 to -4 and +2 to +4. It's close to, it's not quite. And your Z statistic, which is blue, is over here on 4. So since your Z statistic is greater than 1.96, then that means you have to reject the null hypothesis in favor of the alternate hypothesis. So that is letting you know that the students' scores, there's a significant difference between the students' scores and the national average, because the national average is 70. And so the critical value is, I believe it's -1.96 and +1.96, which is close to 2, because you can't, doesn't say 1.96 on the scale, it just says 2, but you can see that it's not quite 2. So now the next thing we're going to do is we're going to perform a hypothesis test on a t-distribution. So a t-distribution is similar to a z-distribution or a normal distribution, except that it has fat tails. So a t-distribution is a probability distribution that is symmetric and similar in shape to the normal distribution, but has heavier tails. It is characterized by degrees of freedom which depend on the sample size. Testing whether a new testing method improves test scores in a class of 20 students when the population variance is unknown. And then so what we're going to do is we're going to create a hypothesis test using the t-distribution to give you an example. So the first thing that we're going to do is we're going to generate our sample data, and we're going to set the seed. So whenever you set the seed, that means that every time you run the program, the variables are going to be initialized to the same values. And so set.seed brackets 1, 2, 3. And n is your sample size being 20, and mu0 is 70. So our sample scores becomes R norm brackets n, mean equals 74, SD equals 8. So R norm is a randomly sampled normal distribution, and n is the 20 samples. And the mean is 74. So you can see right here, because we're creating this data, so you can see right here that the mean of the sample is going to be greater than the mean of the population, because the mean of the population is 70, whereas the mean of the sample is 74. And your standard deviation is 8. So we're going to perform a one sample t-test. So t-result becomes t.test bracket sample scores, comma, mu equals mu0, comma, alternative equals greater. So you're going to do a t-test on the sample scores with a mean of 70, and that's your population mean, and alternative is greater. And then we're going to print out our test result. So our test result is your one sample t-test. So t equals 2.95, the degree of freedom equals 19. And the reason why is because the sample size is 20 and your degree of freedom is calculated as n minus 20. Your p-value is 0.00411. So we normally have a confidence level or significance level of 0.05. And since 0.00411 is less than 0.05, that tells us that we're going to reject the null hypothesis in favor of the alternate hypothesis. So the null hypothesis is going to state that there is no significant difference between the population mean and the sample mean. And the alternate hypothesis tells you that there is a significant difference between the population mean and the sample mean. So in this instance, it's going to be selecting the alternate hypothesis where the true mean is greater than 70. So you have a confidence interval of your 95% confidence interval is 72 to infinite, and your sample estimates with the mean of x is going to be 75.13299. So x is going to be, I think it was 75.13299, whereas when we generated our simulated data, we wanted a mean of 74. So the the mean of x is 75, which is slightly greater than the mean that we wanted, the mean that we set it up for, being 74. So now we're going to plot the t-test and the t-distribution. So we're going to extract the values. So t-stat, that's your t-statistic, becomes t-result $statistic. And then if t is greater than the critical value, reject the null hypothesis. So we can see that from looking at the report that's been generated, that your t-statistic is the t-statistic is 2.95. And it's greater than the critical value. So let's just see what we've said the critical value is. So the critical value is about 1.96, and your t-statistic is greater than, the critical value is 1.73, and the t-statistic is greater than 2.95, so you're going to reject the null hypothesis. And then DF, see if I can find the critical value, but DF is your degree of freedom equals t-result $parameter, but we've already said that the degree of freedom is 19, and the reason why that is because the degree of freedom is calculated as the number of samples minus 1, or the length minus 1. So the length of the samples is 20. So number of samples minus 1 is 20. And then, so now we're going to have our crit. Crit becomes QT, that's quantile T, bracket 0.95. So that means it's going to be the quantile of T, 0.95, and your degree of freedom. And that is your one-tailed critical value. And so we come over here to our one-tailed critical value, and you can see that the critical value is 1.73 after we've calculated that in R. And now, after we've done that, we're going to plot the t-distribution. So we're going to put a curve, brackets dt, so that's the density curve in the t-distribution, brackets x, comma, df. So x is your sample, I believe it is. X is your sample squares, I believe. And df is your degree of freedom. I'm just trying to see if I can find out where the x is. Because I don't even see an x in there. But it's saying dt is x comma df. So your degree of freedom is 19. And I personally don't see an x in there. But you might see an x in there. But I think x is going to be your sample squares. And from -4 to 4, line width of 2. And your main is a one sample t-test, right-tailed, and that's your title. And your x-lab is your label on the x-axis, is your t-value. Y-lab is the label on the y-axis, is your density. And then we're going to shade the rejection region. So x shade becomes SEQ, brackets crit, that's your critical value, comma 4, and a length of 200. And we're going to put a polygon in there. So polygon, brackets C, brackets X shade, comma rev, brackets X shade, comma C. We're going to create another vector, dt, so that's a density curve on your t-distribution, brackets X shade, comma df, comma rep, that's a repetition, brackets 0, comma length of X shade. And color equals light pink. Then we're going to add the observed t-statistic. So AB line equals V equals brackets. V means it's vertical, equals t-stat, that's your t-statistic. Color equals blue, line width equals 2. We're going to add the critical value line. So you've got AB line, brackets, V lets you know it's vertical, equals crit, comma, color equals red, line width equals 2, LTY equals 2, which means it's dashed. We're going to annotate the chart. So we're going to put some text in there. So text brackets t-stat, comma 0.1, comma labels equals paste 0 brackets t equals, and you're going to round the t-stat to 2 points, comma POS equals 4, color equals blue. And then you're going to put some more text in there. So brackets crit, comma 0.15, labels equals paste, brackets critical T equals crit value rounded to 2, POS equals 4, and color equals red. So, and then what that does is that actually creates your plot. And so this is a one sample t-test, which is right-tailed. And so you can see that we have created a density curve in the chart. You can see that your critical value is 1.73, and you can see that your t-statistic is 2.95, and 2.95 is greater than 1.73, so that means that you're going to reject the null hypothesis in favor of the alternate hypothesis. But whenever we created the sample data, the mean of the population was 70, and the mean of the sample data was 74. So we already knew then and there that just for the purpose of this exercise that we were going to reject the null hypothesis. But the mean of the sample turned out to be 75.13299. So the next distribution that we're going to use is the chi-square distribution. The chi-square distribution is positively skewed and used in tests involving variance or categorical data. It is characterized by its degrees of freedom. And then so what we're going to do is we're going to perform a hypothesis test using the chi-square distribution so you can see how to do that. So we're going to test whether the observed proportions of voters by political party match the expected proportions in an election. So how we're going to do that is we're going to create some observed and expected counts. So the observed voter counts is observed becomes C. That's a vector that you create. Brackets A equals 260, B equals 150, C equals 90. So that's your vector. It's going to contain what we just covered. And then your expected proportions is going to be expected prop becomes another vector that we create. So C brackets A equals 0.5, comma B equals 0.3, comma C equals 0.2. So that means 50% of the voters are A. That's what you're expecting. 30% of the voters are B, and 20% of the voters are C. So the next thing we're going to do is we're going to convert expected proportions to expected counts. So expected becomes sum of observed times the expected prop. So that means so then we're going to print expected. So let's come down here and see what the expected is. So the expected is A is 250, B is 150, and C is 100. So that means that A is 10 points less than the observed for A. And it is, so 150. So it's the same as the observed for B, and it is 10 points more than C. So you can see that there's a difference between the expected counts and the observed counts based upon the expected proportions. So the expectation is that you would have 250A, you would have 150B, and then you would have 100C. So, and that's calculated as the sum of the observed times the expected proportion. So the sum of the observed is going to be 250 plus 90 is 350 plus 150 is 500. So you're going to have 50% of 100 is 250 and 30% of 500, no, 50% of 500 is 250, 30% of 500 is 150, and 20% of 500 is 100. So we're going to perform the chi-square goodness of fit test. So your chi result becomes chi-square test, brackets observed, comma, P equals expected prop. So that's your chi-square test. So you're going to use the observed values and the expected proportions. So then we're going to print the chi-square result. And then so if P is less than 0.05, that's your p-value. The observed proportions do not match the expected proportions. So we running our chi-square tests for given probabilities. So the data is observed, and your chi-square equals 1.4, comma, degree of freedom equals 2. The reason why your degree of freedom is 2 is because the number of elements in the vertex, the matrix that you've created, is 3, and 3 minus 1 is 2. So that's how you get your degree of freedom is 2. And then your p-value is 0.4966. So 0.4966 is greater than the significance level of 0.05. So that means that you are going to fail to reject the null hypothesis. You're going to fail to reject the null hypothesis. So if p is less than 0.05, the observed proportions do not match the expected proportions. So since we have failed to reject the null hypothesis, what that means is there's no significant difference between the observed proportions and the expected proportions. And then if we had rejected the null hypothesis in favor of the alternate hypothesis, then that would mean that there is a significant difference between the observed proportions and the expected proportions. So now we're going to plot the observed versus expected counts. So we're going to combine the data into a matrix for plotting. Plot data becomes R-bind, brackets observed equals observed, comma, expected equals expected, and then we're going to create a bar plot. So the bar plot, brackets, plot data, comma, beside equals true, color is a vector of sky blue and orange, main is your title, is observed versus expected voter counts, Y-lab is your label on your y-axis, which is the number of voters, and legend equals true. So we're going to add a chi-square statistic to the plot. So in text, we're going to put some text in there. Brackets, paste 0, so that's sort of like a print command. Brackets, chi-square equals round. Brackets, chi-result, $statistic, rounded to 2 points. Degree of freedom is the chi-square result, $parameter. Your p is your p-value, is significance, brackets, chi-result, $p-value, rounded to 3. Side equals 3, line equals 0.5. And so we've got the chart that we have created. So the observed versus expected voter counts. You have a chi-square of 1.5. Degree of freedom is 2. And p-value is 0.497. So that means you're going to fail to reject the null hypothesis. So your blue is your observed values, and your amber is your expected values. And you can see that in number B, the observed and versus the expected is the same, but in number A, it's slightly different. But according to the R programming, the difference between the observed and expected in A and C is still not that significant. So it failed to reject the null hypothesis. So the last one that we're going to talk about is the F distribution. So F distribution is used in a hypothesis test that compare variances or involve multiple groups. It is positively skewed and depends on two sets of degree of freedom, being the numerator DF1 and denominator DF2, testing whether the average monthly sales differs across the 3 regions in a company. And so we're going to perform a hypothesis test with the F distribution. So the first thing we're going to do is we're going to create some data. And so we're going to set our seed. So when you set the seed, it enables the variables to be set up to the same values every time you run the program. So you have set.seed brackets 1, 2, 3. So region becomes factor brackets, and then you're going to create a vector rep bracket C ABC each equals 20. So you're going to have 20 A's, 20 B's, and 20 C's. And then your cells is going to be another vector that's going to have three values in it. Our norm is a randomly sampled normal distribution of 20 elements in the sample, the mean of 100, the SD of 10, that's your standard deviation. So that's for your region A. Region B is going to have a length of 20 samples, mean of 110, standard deviation of 12, and number C is going to be a mean of 105 and a standard deviation of 11. So you can see the randomly sampled normal distribution is going to have 20 elements in each distribution. So the data becomes data.frame region.cell. So we're going to create a data frame for this test. And we're going to create a one-way ANOVA F-test. So an ANOVA is an analysis of variance. And what the analysis of variance does is it allows you to check 2 or more samples. And in this instance, we're going to check 3 samples. So the ANOVA result becomes AOV bracket cells. You got a squiggly region, comma, data equals data. So you're going to, and then the summary of ANOVA result. So we're going to come over here and print our ANOVA result. So this is your ANOVA result. Your region has your degree of freedom of 2. And as we've already said, that there's 3 elements or 3 samples that you're testing. And so 3 minus 1 is 2. Your sum of squares is 643. Your mean squared is 321.5. Your F value is 3.165. And your P value is 0.497. So that tells you that the 0.497 is less than 0.05. So that means, yeah, I know it's close, but in theory, the p-value should be rejected. The null hypothesis should be rejected in favor of the alternate hypothesis. And then you've got your residuals being 57 degree of freedom, 5789 sum of squares, 101.6 mean square. So since our p-value is 0.497, that's less than 0.05. So in theory, we should reject the null hypothesis in favor of the alternate hypothesis. And then basically what it is the null hypothesis states there's no significant difference between the samples, the means of the samples. And the alternate hypothesis states there is a significant difference between the means and the samples. So you can see that the samples that we have created, you had 100, 110, and 105. So there is a slight difference. And because the p-value was just under 0.05, we're going to reject the null hypothesis in favor of the alternate hypothesis. So now we're going to extract the F statistic and degrees of freedom. F value becomes summary brackets ANOVA result brackets $1 F value 1. And DF1 becomes summary brackets ANOVA result brackets $1 df1 between the groups, and df2 becomes summary brackets ANOVA result brackets $1 df2 within groups. And then we're going to create a box plot using this data. So box plot bracket cells, you've got squiggly region, data equals data, and then so you've got color is going to be a vector with sky blue, light green, and orange. Main is going to be the title. It's going to be monthly sales by region. XLab is your label on your x-axis. It's region. YLab is your label on your y-axis, which is monthly sales, and not equals true. So we're going to add the ANOVA F statistic to the plot. So we're going to put some text in there. So text brackets paste. Paste is like a print command. Brackets F equals F value rounded to 2. DF equals DF1. And then and DF2. The P is your P value, and it gives you the P value from the significant bracket summary brackets ANOVA result brackets 1 PR greater than F brackets 1 comma rounded to 3 points. Side equals 3, line equals 0.5. So these are our box plots that we have made with your monthly sales by region. So F is 3.17, DF is 2.57, and P value is 0.497. And so you can see you've got sales regions A, B, and C. Sales regions A, B, and C. So you can see that the means or the medians, because with a box plot, you can see that your second quartile is the bottom of the box, and your third quartile is the top of the box, and the median is the third quartile minus the second quartile, and that gives you your median. And then your fourth quartile is the top of your box, giving you the outliers. And so you can see here that the means and the medians are slightly different from each other. And so that's why you have to reject the null hypothesis in favor of the alternate hypothesis. So that concludes this video on distributions used in hypothesis testing. I hope that you got something out of it, and the next video is going to be on some more statistical topics, and I hope that you decide to watch it.